the result that I stated last time. So remember that Wn is the renormalized partition function of our polymer model. So it's just the expectation with respect to a simple random walk of exponential sum from n equal 1 to n beta omega n xn minus lambda beta. Okay, where lambda beta is the log Laplace transform of the environment. So this is okay. Our theorem goes as follows. So so the first thing was that our sequence admits a limit P almost surely. Okay, the second thing is that either this limit is positive with probability 1 or it's equal to 0 with probability 1. Okay, and it has expectation 1 if it's not uniformly equal to 0. Okay, so here 1 okay, this having beta c such that P of W infinity beta omega positive is equal to 0 if beta belongs to no, 0 beta c and 1 if beta larger than beta c. Okay, and I'm going to prove this with an open bracket here. Okay. Okay, and let me add two things. Okay, so first, beta c is positive if d larger than 3. Okay, and beta c is equal to 0 if d is equal to 1 or 2. Okay, so this guy a priori belongs to 0 infinity. Okay, okay. Today I'm going to prove the existence without discarding the fact that it can be equal to plus infinity, but we are going to see later that it's fine. Okay, and yeah, it being equal to infinity isn't okay. It's not really a super problematic issue. Is the result clear? Okay, so while I'm proving the result, I will also display the authorship. Okay, so the proof I'm giving is not necessarily the original one, but okay, so. So the first result is due to Boltzmann in 1989, and it's basically the observation is a martingale. And is non-negative. Hence, it converges almost surely. Okay? So we have proved last time that it was a martingale. So. Okay, so now let's move to B. Okay, and okay, let's start with this is A and this is B, and I think that A is quite old. I mean, A is some kind of immediate argument, but let me detail this a little bit. And I think basically it's also B89. Okay, so I mean we are trying to prove that an event has probability 0 or 1. So basically we want to use Kolmogorov 0 or no. Okay, let me write this cleanly and in a way that we can use also later on. So I'm going to introduce two notations. Okay, the first is a point-to-point partition function. So beta, okay, it's just the same thing as before. Except that I'm restricting to trajectories that end up at x. Okay? So in particular, I have that Wn beta omega is equal to the sum over x in dt Wn beta omega x. Okay, the reason I put a hat here is, well, this is a function of x, this is a number, so when I write this without the x, it's just a function. Okay, and this way I can differentiate between the two. Okay, and then I define something else, which is a shift operator, okay, that we have seen earlier for random walk in random environment. So if I have k and z in zd, theta kz of omega, well, it's just omega, but with the coordinates shifted. Okay, so, and finally, yes, I let theta act on functions of the environment. So this is just the composition of f with theta. Okay, so what's the claim? I want to establish. So the claim is that Wn plus m, and let me drop the indices for a moment, it's equal to the sum over x in ZD of the point-to-point partition functions time the shifted partition function. Okay, I mean, the idea here is that if you have a random walk trajectory with n plus m steps, well, first it does n steps, and it ends up somewhere. And then it does m steps, starting from where it ended. So, okay, so there's nothing super mysterious about that, but let's write a detailed proof, okay? So what we have is the sum over x in okay, w and m. Okay, it's an expectation. So I'm just going to rewrite this expectation as the sum over x in ZD. Blah, blah, blah. Indicator x n equal x. Okay, I'm just decomposing the partition function according to where I end up after n steps. Okay, so perhaps a better way to write this would be sum over x in ZD, expectation. Okay, so first I have the this thing, and then I have the indicator, and then let's put m here. M equal n plus 1 to n plus m. Okay, where here I have the usual term. Okay, so now what I want to do is I want to rewrite this term, okay, to make the factorization possible. So basically, I want to rewrite this term to make appear that it's independent of this one. And when I mean independent, I mean here's the only randomness which you are concerned with is the one of the random walk. Okay, omega is fixed. Okay, so, well, what is this thing? Sum of m equal n plus 1 to n plus m. Okay, beta omega n, well, mxm. Okay, so I want to rewrite it. Okay, and I will place myself on the event xn equal x. Okay, because I can do this. I mean, I just need equality on this event because I have the indicator. And I will use the notation xn equal xn plus k minus xn. Okay, and what we have is that xn, k, k larger than 0 is independent of, well, okay, is a simple random walk, symmetric simple random walk, independent of xn and equal 1 n. Okay, I mean, the random walk has independent increments. This is a function of the first n increments. This is a function of the other increments, so they are independent. Okay, so with this in mind, this is equal to, well, the sum from, say, well, n prime equal 1 to n beta omega. Okay, so here I am making this change of variables. So here I will have n plus n prime. And here I will have xn n prime. And here I have to add xn, but xn is equal to x plus x. Okay? Okay, so this thing here, okay, in particular, it's independent of xn and equal 1 to n. Okay, so that's very good. We have two functionals here, okay? One here, one there, and they are independent. So I can factorize the expectation, which is exactly what I want to do. This thing is equal to the sum over x in ZD. Then I have, well, the expectation of exponential blah, blah, blah. Well, okay. Sum n equal 1 to n, blah, blah, blah. Indicator xn equal x. Okay, and then I have a second term, which is the expectation of exponential sum from. Okay, now let me replace n prime by n just to make things more readable. N equal 1 to m beta omega n. Okay, n plus n and xn plus x minus lambda beta. Okay. So this thing here, it's equal to w and x. Okay, it's just the definition. Okay, now the second thing, well, this thing is a simple random walk, so I mean, whether I put n or not, it doesn't change anything. Okay, it's the only variable I'm integrating with respect to. So now I just have a partition function, but except that instead of the original environment, I'm seeing the environment shifted by n in time and x in space. So this thing here is equal to theta and x wn. Okay? In Wm, it's a function of omega. And basically, I'm saying that theta is acting on functions by composition on the left. Okay, this is the definition of this notation. Okay, so any question about this proof? Okay, so now I'm going to use this claim to prove first my 0-1 law and also the fact that the limit being positive almost surely is actually equivalent to having uniform integrability. So to having the expectation of the limit being equal to 1. Okay, so what? How do you prove the 0-1 law? Well, what we have is that Wn positive, it's actually the same thing as there exists an x such that theta and x. Okay, so sorry. Okay, so okay, a consequence of this thing is that well, you just fix n, you make m tend to infinity. Is that so? Well, on the left-hand side, you obtain W infinity. On the right-hand side, you obtain this thing. W infinity. I'm just making m. I'm just making m tend to infinity.
What is Wn?
It's over there.
Okay, but where is the n? Is the limit? Is the limit?
The limit is when m tends to infinity. Okay. Perhaps this is a problem. Like this letter is m, not pi. It's m, and this is n. Okay, but is this okay now? Does this clear the doubts? And yeah, I mean, like here, yeah, I mean, you know that for fixed n and x, this converges almost surely. And here you have countably many of them, so they all converge almost surely simultaneously. So you have no trouble in this. Okay, so as a consequence, basically, in order to have W infinity larger than 0, okay, this is a curly bracket. Okay, let me write this as an equivalence. This is the same thing as having n and x such that theta and x W infinity is positive. Okay. Sorry. There exists x in V for n fixed. Okay? Like this thing is positive if one of the terms of the sum is positive. And this thing here, I mean, remember that omega is bounded. Okay, omega cannot be equal to minus infinity. Okay? This is an assumption we have taken. Yeah, so yeah, this is okay. If one of these things is positive, then the sum has to be positive. No. Okay, there exists an x1 smaller than n. Okay. Sorry. You need this thing to be positive, and for this, you need this event to have non-zero probability. So you need the one norm of x to be smaller than. But it doesn't matter, because this is not what the argument is based on. Basically, the good thing here. Okay, so in fact, here I'm saying these things are equivalent. It's not completely true, you know. These two events, they are not exactly equal. It's only that their symmetric difference has probability 0. Okay? So sometimes people write that events are almost surely equal. Well, it's not really proper, but this is what this means. Like the symmetric difference of these events has probability 0. Because this is true on the event with probability 1 where everybody converges. Okay? I mean, already when I'm writing this, I'm already placing myself on some sub-event on probability 1. Okay. But the important thing here is that this thing here this is independent of Fn. Okay, remember that Fn, it's the natural filtration associated with the environment. It's just all the information that you see up to time n. So it's sigma of omega xn x in zd n smaller than n. Okay? This event here doesn't care about the values of these omegas, so it's independent of Fn. Okay? On the other hand, W infinity larger than 0, okay, is measurable, well, with respect to F infinity, which is okay, I'm just defining it now, which is, well, the smallest sigma algebra that contains all the Fn's. So it's just sigma of the union. Okay, I mean, this is just the product sigma algebra with respect to the environment, and yeah, this is basically the standard thing you work with, and you can check that all the events that you can think of, they are measurable to this with respect to this. Okay, so. Okay, this thing implies that this event is independent of itself because, well, it's independent of Fn for every Fn. So it's independent of the sigma algebra generated by the union. And therefore it's independent of itself. Okay, I mean, if you want to prove this formally, you can say, well, it has to be well, because it's in this sigma algebra, it's well approximated by something in Fn, and because it's independent of. Okay. So in particular, the probability of W infinity larger than 0, it's equal to the probability of equal to okay, yeah, so again, here and there are a few things that are improper because basically, because the limit exists almost surely, as soon as I'm writing events, I should write them in other way, like the limit exists and this occurs. And then some crazy thing can happen, so it might be possible that this limit here exists. Okay, so that this limit here exists, but it's due to some compensation there, and these limits, I don't know. So, but there is nothing interesting going on there. You can place yourself on this subspace of probability 1, and then things behave nicely. Okay, so this is the 0-1 law, and now we are going to use, okay, this thing to prove uniform integrability. Well, to prove that if the limit is non-degenerate, okay, then you have uniform integrability. Okay, so where is this? Okay, so if okay, and this result here, this is due to Comets and Yoshida. And 06. Okay, so let's use this identity. And what we are going to do is we are going to take conditional expectation with respect to Fn. Okay? So, well, we can put the conditional expectation inside the sum using Fubini. So, okay, this thing, it implies that the expectation of W infinity knowing Fn is equal to the sum over x in ZD. Then you have W and x. Okay, let me write this. Expectation W and x, theta and x, W infinity knowing Fn. Okay, but this part is measurable with respect to Fn. So I can take it out the expectation. This part is independent of Fn. So this is just a pure expectation. Okay, so what I get is the sum over x in ZD, Wn x times the expectation of theta n x W infinity. Now I have translation invariance, so this thing doesn't matter. And therefore, when I sum here, I get Wn. So I get Wn times the expectation of W infinity. Okay, so what I would like to do now, okay, is to send n to infinity. Okay, here I get W infinity. Here I get W infinity. And you see that this has to be equal to 1 because W infinity is not equal to 0. Okay, but there is something not nice about this, is that if you've not seen martingales, or if you don't remember it very well, well, this is actually a non-trivial result of martingale theory, that this tends to W infinity. So let's, just for the sake of it, okay, let's do it a different way. It's not much longer. But okay, it's a bit convoluted, but okay, so this is positive, okay, by assumption, because we know that well, this is what's inside is positive with positive probability. So what we have is that Wn is equal to E W for infinity over Fn dividing by E W infinity. Okay, so now what I'm claiming is that okay, and important thing. Okay. We already know that this is smaller than 1, okay, so you have no problem. In particular, it's integrable. You have no problem in defining conditional expectation. Okay, but what's important here is that if x belongs to L1, then E of x knowing Fn is uniformly integrable. And that's not only for filtration, that's for an arbitrary family of sigma algebras. In fact, you don't need this family of sigma algebras to be countable. Okay, like the set of conditional expectation of x with respect to anything, this is a uniform integrable collection. Okay, so let's admit the lemma and conclude. So, well, if this is uniformly integrable, well, Wn is uniformly integrable, and we've concluded. Okay, so let's prove the lemma. So, okay. What we need to show is that if you, okay, let's call this xn. And you need to show that if you integrate xn against an event of small probability, what you get is small. Okay, uniformly in n. Okay? So we need to show that if PA is smaller than delta, then delta of epsilon, then the expectation of x indicator of xn indicator of A is smaller than epsilon for every n. Okay, and well, xn you can write it as x. Okay, xn. You can write it as the expectation of x larger than m, plus the expectation of x. Okay, let's put x smaller than m. Okay, so this one is xn1, this one is xn2. Okay, and this, okay, so the expectation of xn2 index A well, it's smaller than m times p of A. Just because xn2, okay, the absolute value of xn2 is smaller than m, okay, just because it is, you know, just by comparison. Okay, this thing is smaller than m in absolute value, so the expectation, the conditional expectation is smaller than m in absolute value. Okay, and the expectation of xn1, indicator of A, well, it's smaller than the expectation of xn1. Okay, which is smaller, okay, just by Jensen, than the expectation of x indicator than x is larger than m. Okay, what I'm doing is here, I have the expectation of the absolute value of this, but the absolute value of this, I can just put the absolute value inside, and then I have the expectation of the conditional expectation, which is just the expectation. Okay, so now this is smaller than epsilon over 2 if m is large. Okay, but this does not depend on n. Okay, and now I take delta is equal to 1 over, well, epsilon over 2 m epsilon, and I'm done. Okay? The expectation I'm trying to bound is smaller than the sum of these two things, and both things are smaller than epsilon over 2. Okay, and this is not superfluous. This is really one of the things you need to prove that the limit of this is W infinity. Okay, so. Okay. So I think we are done with B, and we have to prove C. So C is C is monotonicity in beta. Okay, meaning that I want to prove that basically, yeah, like if yeah, so. Okay, so I want to show that the function that to beta associates the probabilities that W infinity is positive, that it's non-increasing. Okay, because I know that this thing can assume only two values, well, this tells me that, well, it has to be 1. Okay, I know that it's 1 at 0. Okay, and then it has to be 1 until somewhere, which I will call beta c, and then 0. And okay, I mean, I know it's 1 or 0 there, but this thing does not tell me anything about what happened at the critical point. Okay, so this thing is also due to Komatsu and Yoshida. In the same paper. Okay, I'm going to present a proof which is okay, a bit similar to the other one, but I'm going to need to introduce a notion for this, which is a notion of convex ordering. Okay, so okay, let me define M1 to be the set of mu in P of R. Okay, so P of R is a set of Borel probabilities on R. So the set of probabilities which are such that, well, okay, the distribution has finite mean, okay, and more precisely, it has mean equal to 1. Okay, so the 1 is not really important here. I could put anything, but we are going to apply this for probabilities with mean 1, so let's put it there. Okay, and now I'm going to define an order on this set. Definition. Given mu and mu prime in M1, we say that mu prime convexly dominates mu, okay, and I will write mu prime if for all phi from R to R plus union plus infinity convex, the integral of phi x mu prime dx, well, okay, integral of phi x mu dx is smaller than the integral of phi x mu prime dx. Okay, is it clear what the definition is? Okay, let me give you a few clues about the definition, perhaps. So first, I have fixed the mean here. It's just for convenience. You could define this on the whole set of integrable of probabilities with finite mean. Okay. But the thing is that as soon as two measures have different means, they are not comparable. Okay, so if you want, you can already separate the set of measures with finite mean in classes that are not comparable. Okay, it's just because here in your convex functions you can add linear corrections and they will make things, okay, so they can make things change in one way or another if you have nu and nu prime with different means. Okay? So the second thing is that, well, you have lots of convex functions, but you don't have so many things to check here. Okay, so mark. It is sufficient that star is satisfied for x minus a plus. For all a in R or for all a in a dense set. Okay, so why is it true? Well, it's just that if you have a convex function, then you can always approximate it in an increasing fashion by a function which is piecewise affine. Okay, so if I have a convex function, I can just approximate it in an increasing fraction. Okay, so this is phi and this is phi n, and phi n is going to increase to phi. So this phi n here, it's a linear combination of these things. Okay, so then if it's true for, if this is true for all this is true for every phi n. If it's true for every phi n, it's true for every phi just by monotone convergence. Okay, and perhaps another remark. Okay, what does this measure? What does this mean? Basically, being convexly larger than another measure, it means that in any sense, like mu prime is more spread out than mu. Okay, so now let's see examples. Okay, and I will give you okay, and okay, so this is one. And perhaps yeah, a second remark, if x is distributed like mu and x prime is distributed like mu prime, we will write okay, if I write a convex comparison between random variables, well, it's a convex comparison between the corresponding distributions. Okay, but it's more natural to define the order on the distributions because if you remember the definition of an order, well, this is not an order on the set of random variables because basically, yeah, I think for an order you need that if you have the inequality in both directions, then things are equal. And here, if you have inequalities in both directions, then things are equal in distribution. So they are not equal as random variables. Okay. So yeah, no, let me tell you about examples. So okay, perhaps let me consider Mn with, well, M0, okay, with a martingale. Okay. Then Mn is non-decreasing for the convex order. Okay, so why? Well, you know that the expectation of phi Mn plus, okay, this thing, well, it's equal to the expectation of phi Mn plus 1, knowing Fn. Okay, everything is positive, so I don't need to worry about integrability. This is the reason why phi takes value in R plus in my. And then what I can do is I apply Jensen. So this is larger than the expectation of phi. Mn plus 1 Fn. Do I have? Yeah, I think I need a bracket here and a bracket there. And this is equal to the expectation of phi Mn. Okay, so you might say, okay, this is a nice example. But it's more than this. It's actually the only example there is, because okay, and I won't prove you this, but conversely, if mu m is a non-decreasing sequence. Well, okay, increasing is better because for the convex order, then okay, and perhaps okay, yes. Okay, then there exists a martingale sequence Mn n larger than 0 with Mn mu n for every n. Okay, and yeah, okay. The proof of this is surprisingly not super complicated, but yeah, it uses Brownian motion and stopping time. So one-dimensional Brownian motion and stopping time. But yeah, I don't know. Perhaps this gives some value with this to this definition. We will not use it a lot. I mean, we'll only use it to prove this. Okay, but okay. So okay, I told you this is the only example, but I'm still going to give you 2 other examples. So B, okay, so take 1 plus beta x, beta larger than 0, where x satisfies E of x is equal to 0. Okay. So, okay. This is convexly increasing. Okay, so how do you prove this? Well, you take phi that grows up at most linearly, okay, just for things to be in L1. Okay, but this is sufficient to prove it for phi that grows at most linearly. Okay, so let's take phi. Okay, you want phi of x smaller than Tx when x goes to infinity, and phi belongs to C1. Okay, but again, by density, this is sufficient to show. So what you have is that, well, the derivative in beta of the expectation of phi 1 plus beta x, well, this is equal to the expectation of x phi prime 1 plus beta x. Okay, I'm just taking the derivative inside. And now I'm claiming that this is larger than 0. Okay, so why is this larger than 0? Okay, so phi is convex. Okay, this is something I didn't tell you, but phi is convex, of course. So this thing is an increasing function of x. Okay, so I have the expectation of a product of two increasing functions. Okay, so if mu is a probability, f and g are increasing. Okay, and let's assume, for instance, that okay, perhaps either in L2 or non-negative. I want things to be well defined. Okay. Then the expectation, then the integral of f u g u mu d u is larger than the integral of f u d u g f u d mu. Okay. D mu. Okay, and then if you apply the lemma, this 0 here, it's nothing more than E of x, E of phi prime 1 plus beta x. Okay, so increasing function of the same variables, they are positively correlated. That's an important result. Okay, and do you know how to prove this? Sorry? Yes. You can do, so you can basically do an independent coupling. So, well, if you write it just using integrals, okay, basically what you're saying is that, well, you're looking at the fu minus gu, fv minus gv, mu du, mu dv. Okay, you look at this thing, and this thing you can say, okay, I know that f and g are increasing, so I don't know about the sign of this or the sign of this, but it has to be the same. Yes, f minus f of v. G of u minus g of v. Sorry, yes. Because if not, there was absolutely no reason why it would be the same. So yeah, this has the same sign as u minus v, so both things have the same sign. Okay, so this is larger than 0. And now you just expand the product here. Well, on the positive side, okay, you get fu gu fv gv. Okay, and then when you get fu gu, well, when you integrate with respect to v, it's a probability, so you just ignore this. Okay, and integrating, well, so you get twice this term, so twice f g d mu. Okay, just from these terms. And then you get two negative terms, which are these ones, fv-gu and fu-gv. Okay, and in that case, you're integrating against the product measure. So you get minus 2 integral of f d mu, integral of g d mu. Okay, and okay, proving this, yeah, it kind of makes the point that, yeah, convexly increasing, it really means that your probability is more spread out, okay, on one side than on the other. Okay, okay, and let me give you a final example, which perhaps will be the most interesting one for our purpose. Well, exponential beta omega 1, 0 minus lambda beta, beta larger than 0. Okay, so this is convexly increasing in beta. Some question? No? Sim. Okay. Okay, so third family of example. Yeah. So when I'm saying there is only one example, well, here basically, well, if you have a family of increasing beta, basically, by changing, okay, the joint laws, you can make this a martingale. Of course, this is not a martingale if you take an increasing family of beta, but you can keep the marginal laws, change the joint laws, and make this a martingale, okay, which is a non-trivial fact. Okay, this is a trivial fact, okay, or an almost trivial fact only when X is Gaussian. Okay, if you have a family of Gaussian, well, okay, when you increase the variance, okay, you can just make, okay, you're summing independent Gaussians. Okay, so this thing is convexly increasing in beta. Okay, so the proof is the same. Okay, so I'm looking at the derivative of this thing minus lambda beta phi of this. Okay, so I get, well, I have to take the derivative of this out. So I get omega 1, 0 minus lambda prime beta times phi prime beta 1 beta omega 1 0 minus lambda beta. Okay, both of these things are increasing functions of omega. So this is larger than the expectation of omega 1 0 minus lambda prime beta time the expectation of phi prime beta omega 1 0 minus lambda beta. Okay, and the important thing to conclude is to show that this thing is actually equal to 0. Because, well, phi is arbitrary. We have no idea what this might be. So, sorry?
Lambda beta is the log.
Yeah, well, lambda beta is what makes this have expectation 1. So this is the log of the expectation of beta omega 1 0. But I wrote it at the beginning of, well, I wrote it yesterday, but I also wrote it at the beginning of the lesson. Okay, so, okay, why is this equal to 0? Sorry, this is not equal to 0, of course, because I forget about this. Okay, so let's say that zeta beta is equal to exponential beta omega 1 0 minus lambda beta. Okay, and now I'm going to use this notation, and okay, I'm sorry. What I get here is yeah, okay. So here yes, this is because okay, so be very careful with your computations. Okay, I'm taking the derivative of a composition, so I have to take out the derivative of this, and the derivative of this is itself the derivative of a composition, so of course you have to keep the exponential and not only take this thing out. So what you get is really beta omega 1 0 minus lambda, this minus this times this times this. Okay, and this is larger. Okay, because there is a subtlety, so this is something important. Okay, so I'm using this is star with mu equal to, well, d mu is equal to zeta beta dp. Yeah, because I'm just considering this as a probability density. Because if not, this wouldn't be an increasing function. Yeah, if I didn't do that, I would have to lie about increasing functions, and I don't want to do this. But this is increasing in omega, if you can believe me. And this is increasing in omega as well. Okay, so I just need to check that this is equal to 0. And the reason is simply that, well, if I look at lambda prime beta, well, it's the derivative of log beta omega 1, 0, just by definition. And this thing, well, it's just the derivative of exponential beta omega 1, 0 divided by this. Okay, just derivative of a log. And this thing is nothing more than the expectation of omega 1, 0 exponential beta omega 1, 0 divided by exponential beta omega 1, 0. Okay, but this thing here is zeta beta. Okay, so wait. Oh yeah, this is true. Okay. And this is lambda prime beta times the expectation of zeta beta, of course, because this is a... Okay, so therefore, what I'm saying here is that, yeah, this expectation here is equal to 0, just subtracting both ends. So far, so good? Okay, so the important takeaway here is that, yeah, when we increase beta, basically, well, the variables that we put in our partition functions, okay, so they are the zeta betas, in fact, because we are taking exponent. Well, we are taking product of the zeta betas, okay, at different sites. So these variables are convexly increasing. So therefore, when you apply convex function, the expectation will increase. So if you apply concave functions, expectation will decrease. Okay, so what we need basically is okay, we need to make this a concave function, therefore, because we want something decreasing. Okay, and we need a multivariate version of the. I mean, the definition of the convex order gives us something for one variable. We need some kind of multivariate version of this. Okay, so let me write this multivariate version, and then we will okay, we will see how to make this to replace this by a concave function. Okay, so yeah, I think this is not more than a lemma. So if phi from R to R plus, okay, Rm, okay, so let's say m is larger than 1. Now you have a function of m variables, and I'm not saying that this function is convex. I'm saying that such that, okay, let me write it, for all I, for all x1, xi minus 1, xi plus 1, xm, phi x1, xi minus 1, xi plus 1, xm is convex. Okay, so yes, the claim is just that the assumption is just that phi is convex in each individual variable, but not jointly as a function on Rm. Okay, and in that case, okay, so let's assume that zeta I equal 1 to m are IID with distribution mu zeta prime I equal 1 to m are IID with distribution mu prime. Mu is convicted. Okay. Okay, if A, B, C, then what is the expectation of phi zeta I equal 1 to m? Well, it's smaller than the expectation of phi zeta prime I equal 1 to m. Okay? In fact, you can go a bit further, but the idea is that if you have a function which is convex in every variable, and you apply it to IID random, to independent random variables, basically the expectation will increase if you change the marginal of the variables in an increasing way for the convex order while keeping independence. Okay, so this is quite reasonable. And the proof is really a direct consequence of the definition of the convex order. So the proof is by induction. M equal 1 is just the definition of the convex order. Okay, so now let's do M implies M plus 1. Okay, so if you look at the expectation of phi zeta 1, zeta m plus 1, knowing zeta m plus 1, okay? Well, if I'm conditioning to the last thing, then basically I'm just fixing this value, okay? Now, when I look at this as a function of m variables, well, it satisfies my assumption. Okay, so by the induction assumption, what I can do is I can replace all these things with psi prime. So okay, and on the other hand, so this is 1. On the other hand, if I look at this thing, okay, here, okay, I have to tell you what the Okay, here I'm writing zeta prime and zeta under the same expectation, so I'd better tell you how they are coupled. So I'm just coupling them in an independent fashion. Okay, so now if I conditioning this with respect to zeta prime I, well, I'm fixing all these things. So I'm just using, I'm just having a convex function of one variable. Okay, so I can just apply the definition. And I get that this is smaller than the expectation of phi zeta prime 1, zeta prime n plus 1, knowing zeta prime I equal 1 to m. So this is 2, and well, now I'm just combining 1 with 2. I'm taking the expectation of 1 and the expectation of 2, and this gives me the right thing. Okay. So now let's finally prove this. So yeah. So now comes a bit of a okay. So let's prove this. What I'm going to do is to prove something a bit different. I'm going to prove that is non-increasing. Okay, and well, this is sufficient because this is sufficient, okay, because I just have to take beta c to be the inf of beta such that the expectation of square root of W infinity is equal to 0. And I'll be good because, okay, if beta is larger than beta c, then W infinity is equal to 0 almost surely. And if beta is smaller than beta c, then, well, this thing is positive. So therefore, the probability that W infinity is positive is positive. Okay, and because it's positive, it has to be equal to 1 because the two available values are just 0 or 1. Okay, and now what we just need to prove is that really that put a beta here, is non-decreasing, non-increasing. So I just need to prove it for finite n because this thing is just the limit of that. Okay, this thing is just the limit of that simply because square root of Wn is equal to 1. Okay, so you have a sequence which is bounded in L2, so it's uniformly integrable. So therefore, if it converges, almost surely it converges in L1. So. Okay, so let's prove this. Okay, so perhaps how do I make this? Yeah, okay. What I'm going to consider really is square root of Wn minus AWN. Okay, minus Wn minus 100. Okay, I'm going to show that this is decreasing. Well, simply because I want a function which is negative, so that I have a concave function, so I want that the opposite is a convex function which is non-negative. Okay, so it's just for the sake of making it negative. Okay, well, okay, this, but this is exactly the same because so now okay, so I take phi x is equal to square root of x minus x minus 100. Okay, phi x is equal to x plus 100 minus square root of x. Okay, this is if x is positive, and infinity if x is negative. Okay, so I just have to show that phi of Wn is increasing. Okay, so I just have to show that well, phi of Wn actually satisfies this. Okay. So, let me look at it. Okay, I call it phi 0. Okay, so I want to show that the expectation of phi 0 of Wn beta is increasing, okay, or non-decreasing. Okay, so for this, I want to write this function as a phi of the variables that appear inside. So, well, this thing, it's phi 0 of, and then what I have is really, no, okay, I will write 1 over 2d to the n, the sum over x in omega n, and then I have the product from n equal 1 to n of zeta beta, and now I will going to put n xn. Okay, zeta beta n x is equal to exponential beta omega n x minus lambda beta. Okay, now the good news is if you look at this, okay, as a function of zeta, beta, and x for fixed n and x, okay, for fixed n in 0, n, and say x smaller than n. Okay, just to say that we have a finite collection. Well, this is just a linear function. Okay, so then if I write this as phi zeta beta and x, n smaller than n, x smaller than n. Well, this is a function that satisfies this. Okay, just because the marginal here, it's just, well, basically minus the square root applied to some linear function. Okay, so this is just because this term here, it appears at most once in the product. Okay, so the rest you consider it as a constant. Okay, and I think we're done. So we use this lemma and we get that. Okay. So from the lemma, the expectation of phi 0 Wn beta is increasing in beta. Okay, so the expectation of square root of a okay, yeah. Okay, yeah, if you don't like phi 0, I mean, just work with square root, use the fact that square root is concave. What I don't really like is that I've given you a result assuming that everything was positive, and then I'm using it for functions that are not positive. But you know, for convex, I mean, like every convex functions, they are positive, because if you just add some affine thing, then they are positive. So, which is exactly what we're doing here. Okay, so so we have proved A, B, and C. Now, okay, we are going to do. I think it's better to do D on Friday, but D is actually not very complicated. So to prove D, you need to show that if beta is small, you have weak disorder. So you need to show that if beta is small, then Wn is uniformly integrable. Because if you're, well, having weak disorder is equivalent to be uniformly integrable. Okay. So we're not trying to prove something stronger. And to prove that you're uniformly integrable, well, you know that you're uniformly integrable as soon as you have uniformly bounded moments of order more than 1. Okay, so because it's difficult to compute moments of non-integer with non-integer exponents, the easiest thing to try to do is to try to compute the second moment of Wn. Okay, and it turns out that it has a very nice expression, and that you can prove that it's bounded for beta small. Okay, so yeah, like C was proved in the 2000, but like actually D was proved in the 80s. Okay, this is the original Boltzmann result. To prove that, well, you have diffusivity. Basically, what Boltzmann proves is that you have diffusivity for low beta. So he used these martingale techniques to prove that you have diffusivity okay, when W infinity is positive. And then you had to prove that this regime was non-empty. So yeah, using this second moment method, prove that for beta small, well, you know that W infinity is positive. Okay, so see you on Friday. And then I will not prove E yet. We will try to, yeah, I think after proving this theorem, perhaps we will try to explore what weak disorder means and why it means that you have diffusivity. Okay, and then move to the strong disorder case and prove E at that moment. Okay. Any question?
So you had some results from the critical case. Then it's like a value that you can pinpoint in some cases, some dimensions. So how do you get that result for the critical?
Okay, so I think in general it's a bit hopeless to hope that you can identify beta C. There are some things you can say about it, and there are like specific cases where you can compute it. So I think what we will do in this class is to explore like this simpler model where instead of walking on ZD, basically you're walking on a tree. Okay. Instead of taking a directed walk on this graph, okay, you're taking a directed walk on the tree. Okay, and this simplifies things a lot. And in that case, basically on the so where your polymer pass. Okay, I mean your pass is just something on a binary tree. Okay. Okay, in that case, you can compute exactly the critical value of beta. Something that we've shown recently is that if you're taking some very specific random walk, okay, so first in dimension 1 and 2, beta C is equal to 0. Okay? And really the fact that beta C is equal to 0 is really related to the fact that the walk is recurrent. Okay? But somehow, yeah, so the fact that the walk is recurrent in dimension 2, I mean, it's because the probability of going back to 0 after n step diverges, but the sum is divergent, but it's barely divergent. So you can imagine walks that are a bit like the two-dimensional walk, but you make it slightly more diffusive in such a way that the probability of returning to 0 is now summable, but due to logs, not to some exponent. Okay, in that case, we are able to say the value of beta C. Okay, so basically, the computation I'm going to give you next time gives you a bound on beta C. This bound is not sharp on ZD. Okay. But if by chance you're somehow like a two-dimensional transient walk, okay, in that sense, okay, and okay, there are some assumptions, but then the beta critical is actually the bound you get from the second moment down. So, but this is something very specific. In general, okay, what you can say is that basically beta C is the point at which the expectation of Wn beta 1 plus 2 over d starts, oh well, diverges. Okay, so basically, if you look at this thing, okay, if you put a P here, the point at which this will start to diverge, it will depend on P, okay, and it will increase when P decreases, okay, until that point, which is a critical point, okay. So, yeah, basically because when D is equal to 2, this is equal to 2, so this is something you can compute explicitly. When D is not equal to 2, then you cannot compute. Okay, so this is the reason why if you want to have an example where you compute things, you need to have a walk for which the effective, which is transient, because you don't want beta c is equal to 0, and for which the effective dimension is 2. Other questions? Okay, so see you on Friday.